Hi everybody, we are in section 5.1, so we're moving on to chapter 5. Like I mentioned last time in 4.7, our conversation on antiderivatives, we will be using that concept later on in this chapter, but not quite yet. So we're going to put that on hold for just a couple sections here while we start talking about the concept of areas, an area under a curve, and then look at a little bit of application into distance. So the main objective for us in this chapter is we're trying to be able to determine area under a curve. So suppose that f is a continuous function. We'll assume that it's positive for now on the interval from a to b, so its graph lies above the x-axis. We want to find the area of the region that lies under that curve and above the x-axis between a and b. So we're looking for this whole region in here. Okay, so we want to try to determine area under that curve, and we're going to look at different methods we have for doing this. Starting off today, we're going to be justifying kind of how this process comes about, like how we go about doing this in a more methodical way, and then in future sections we'll be looking at faster and shorter ways of computing it, kind of like when we did derivatives, right? We learned the more technical, precise way of doing it first, and then we learn kind of the more fundamental rules that help us solve them more quickly afterwards. Okay. So we start off by dividing the interval from a to b into n equal subintervals of width delta x. So basically we're taking the entire interval and we're splitting it up into pieces, okay, into separate parts of equal width. So that's going to look something like this. Okay, so we have down here x sub 0 is going to be our first value, that's our a value, and then it just starts counting up to x1, x2, etc., all the way up to x sub n, which is our b value. Okay, and we can divide it into as many subdivisions as we want, and these are all equally spaced subdivisions. Okay, so what we're going to be doing here is I'm trying to identify the area, again, of this entire region, but with a lot of curves, we're not able to really do that. So what we're going to do instead is try to, as closely as we can, approximate the area of each of these strips here, and then just take whatever those areas are, and then add them all up together, and then that result gives us a good approximation for the entire area under this curve. Okay? So how are we going to do that? Well, we're going to be using shapes that we are more comfortable working with, because curves do not play nicely when we're trying to find area. So we're going to use something a little more geometric. Particularly, we're going to be using rectangles. Okay, so we're going to be approximating the area of each of these strips using rectangles. So here they give us a couple of sums. I want to come back to this in just a second. I want to show you kind of what we're doing first. Okay, so here's each of these strips. So we're taking each strip and we're turning it into a rectangle, and the rectangle's height is going to be determined by one of the sides of the rectangle. So here we're going to be talking first about the left-hand sum. So the left-hand sum. Okay, so this is often abbreviated LHS. So in this case, I took the first x value down here, so x naught. I used its height for the height of my rectangle. And then, of course, the width of the rectangle, the width for all of these is just delta x, right, etc., for all of these. So I can use that to get this area. And then do the same thing for the next one. Use that left-hand x value, okay, find its height up here, and then use that to compute the area. Do the same thing for this one, for this one, for this one. Okay, so we're just finding the areas of rectangles, right? So width times height, and we're doing that as many number of times as we need to. And what that's going to give us, if we come back up here, that's this formula right here for the left-hand sum. This is also abbreviated LN, L sub n, where n is the number of rectangles that we're using. Okay, so but each of these pieces, so like this piece right here, so the f of x sub 0, that's going to be the height. Let me make this a little thinner. So that's going to be the height. Okay. And then the delta x, of course, is the width. So this whole piece is the area of one of the rectangles, of the first rectangle. Okay. And then we go to the next one, we get the area of the second rectangle. You get the area of the third one, the fourth one, etc., until we get the area of the last one. Okay. Now, in this case, we're using f of x sub n minus 1 for our last rectangle, because if we go back to the graph, because we're using the left-hand endpoints, that means we're using this value to determine the height of the last rectangle, and that's corresponding to x sub n minus 1 here. Okay, so that gives us the height of this last rectangle. All right. Now, the other one that we're working with is the right-hand sum. So for the right-hand sum, we still have the same values here going from x naught up to xn, but this time we're using the right-hand side of each interval to determine the height. Okay, so we're starting on the right and then using that to draw the rectangle, and we're doing that for all of these. See, we're using the right-hand side to determine height, and then get the area of each rectangle, and add them up. And that's going to give us this formula right here. So that's the right-hand sum, also abbreviated r sub n. Okay, and again, we get the same thing. Notice we're not starting at x sub 0 this time. We're starting at x sub 1. That's because, again, we're using the right-hand side of that first rectangle. Okay, so but this is still the area of a rectangle. And then the next rectangle, etc., all the way up to the very last rectangle, and we are using x sub n in this case because that is the right-hand side of the very last rectangle. Okay. So you might notice if you write a bunch of these out, a lot of the terms are going to be the same, and if you just continued this pattern on, every term in these would match except for the first one and the last one. So this first one here and this last one here. That's really the only difference between these two. Other than that, you're using pretty much the same rectangles, just looking at them from the left and from the right. Okay, so these are the formulas that we're going to be using, so and they kind of go into that whole explanation again here. All right. So let's go ahead and look at an example. So we have the graph of 1 over x on the interval from 1 to 2. Calculate the left-hand and right-hand sums on this interval with n equals 5. Okay, so we're going from 1 to 2. So let's go ahead and do the left-hand sum first. So left-hand sum. Let me make this a little thicker here. Okay, so we're going to split this into 5 pieces, right? N equals 5. So if n equals 5, that means that delta x, right, which is b minus a over n, that's going to be 2 minus 1 over 5, which is 1/5. You can also call it 0.2 if you like. Okay, so we're going to start at 1. We're going to break this into 5 pieces, going all the way up to 2. So let me See if I can make this as even as possible. Three, four, five, perfect. Okay. And then I'm going to be using these left-hand endpoints to create the rectangles. So I'm going to use the height of this one and just carry that over to finish off the rectangle. Do the same thing for this one, for this one, for this one, and for that one. And theoretically, they should all be the same width. Okay. All right. So this is the region that we're trying to find, is these areas in here. So to do that, I need to get the area of each of these rectangles. Okay, so the region in question here, so it starts at 1, and it's going up 1/5 or 0.2. So this next one's going to be 1.2, this is going to be 1.4, 1.6, 1.8, and then up to 2. So to get the area of each rectangle, we're going to do, so left-hand sum, and we have 5 subdivisions, so this is going to be L sub 5. So left-hand sum with 5 rectangles. This is going to be f of 1 times delta x plus f of 1.2 times delta x plus f of 1.4 times delta x, delta x, plus f of 1.6 times delta x, almost had enough space, plus f of 1.8 times delta x. Okay, so each of these represents the area of one of these rectangles. Okay, so 5 rectangles, we got 5 terms here. Okay, so in order to compute this, so we need to plug in these values into the function. Remember the function back here is 1 over x. So let's go ahead and do that. So we've got here 1 over 1 times 1/5 plus 1 over 1.2 times 1/5 plus 1 over 1.4 times 1/5 plus 1 over 1.6 times 1/5 plus 1 over 1.8 times 1/5. Okay. And if you actually convert those decimals into fractions and simplify this, it turns out this actually gives you, so 1/5 plus 1/6 plus 1/7 plus 1/8 plus 1/9. Okay, and then we could get a fraction for this, but it gets kind of ugly. So I'll just give you decimal approximation here. That's 0.746. Okay, so that's our left-hand sum. So this is the approximate area of all of these rectangles up here. So that gives us an approximation for the area under the curve. Now this is not the exact area under the curve, right? And you can see that in our drawing up here. We have a little bit extra area, right, that we're over counting here. So right there, right here, 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 and here. All right, we've gone a bit over. So that tells me that this is going to be an overestimate of the actual area, but that's okay, because we're just approximating at this point. But that was the left-hand sum. So let's go ahead and take a look at the right-hand sum on the next page here. Okay, so same function. Let's go ahead and do right-hand side now. So let me get my interval split up here. Okay. So this time we're going to be using the right-hand sums. So I'm using the right-hand endpoint to determine the height of the rectangle. So wherever the right-hand side hits the function, that's the rectangle. Okay. So again, these areas here are what we're looking for. All right. So our information is still the same, right? N is still 5 subintervals, right? Subrectangles, and delta x is still 1/5, right? Or 0.2. Okay, so for our right-hand sum, or r sub 5, that's going to be, we're going to start not on the left-hand side of the first interval, but on the right-hand side of the first interval. So that's going to be f of 1.2 plus, times delta x plus f of 1.4 times delta x plus f of 1.6 delta x plus f of 1.8 delta x plus f of 2 times delta x. And we actually get to use the furthest, most right-hand endpoint this time, because we're using those right-hand sides. Okay. Now, again, a nice thing about this is all of these terms in here were all used in the previous one. So we already know what all of those are. The only new one here is f of 2 times delta x. So let me just get all of these. Let's see. So these were 1/6, 1/7, 1/8, and 1/9. So 1/6 plus 1/7 plus 1/8 plus 1/9 plus f of 2 is 1/2. And then this is times 1/5, which is delta x, so that's plus 1/10. So it kind of goes along with that pattern there. And this is approximately 0.646. All right. So we get this for our right-hand sum. So what does this tell us? Because, of course, again, in this case, we can see that in this circumstance, my rectangles are a little bit too small, right? I have neglected this area here, some area here, 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 and here. So that tells me this is going to be an underestimate of the actual area. So when we're talking about what the actual area is, it's not just as simple as taking an average of like these two values, but we can use them as kind of boundaries. So we can make a conclusion that the area of that region must be between these two, because one of them was too high, one of them was too low. So it's 0.646 and 0.746. So that is a boundary for our area. So it just depends on how close, how accurate we really need to be in any particular situation to determine if that's close enough, if we've bounded the area enough. Okay. So let's look at the next one here. So this is the same function. Excuse me. Same function on the interval from 1 to 2, but we're going to do a left-hand sum with n equals 10. Okay, so we're going to be doing 10 sub-rectangles here. So if n is 10, then that means that delta x is 2 minus 1 over 10. So that's just 1/10, right, or 0.1. So let me get this interval, and we're going to split this into 10 pieces. So that's 1, 2, 3, 4, 5, 6, 7, 8. Nope. me 4, and then split that again. So this is going to get pretty tiny here. Okay, and we're doing a left-hand sum. So I'm using all my left-hand endpoints to create my rectangles. Oops. Okay, and theoretically these would all be evenly spaced out. Okay, so just cap off my rectangles here. And you can see by the time the curve starts flattening out at the bottom, it's really hard to tell exactly where one rectangle stops and one begins. Okay, so we're going to be getting these areas in here. So we're going to have 10 terms this time. We're finding 10 separate areas. Okay, and then we're going to add those values up. All right, so let's do this down here. So this is L sub 10. Okay. So that's going to be f of 1 times delta x plus f of 1.1 times delta x plus f of 1.2 times delta x, etc. This is going to go all the way up to the second to last value, right? Because we're using the left-hand side, so that's f of 1.9 times delta x. Okay, so this is going to be 1 times 0.1 plus 1 over 1.1 times 0.1 plus 1 over 1.2 times 0.1, etc., etc. And that's 1 over 1.9 times 0.1. Oops. Okay, so we get all those terms. We add all of these up, and this gives us 0.719 approximately. So, and you notice we are still over, right? Up here in the graph, they're getting smaller, right? But we're still over by a tiny bit in each one of these rectangles. So this is still an overestimate of the actual area, but notice that it's lower than what we had before, right? We had 0.746, now we have 0.719. So our over approximation is actually getting a little bit lower, right? It's getting closer to the actual area. So if we were to do the right-hand approximation again with 10 rectangles, then we would see that that one would also get closer as well. So the main thing to note out of this process is the more rectangles we use, the closer our approximate area is going to get to the actual area. Okay, so let me just put that right here. So the more rectangles we use, the closer our approximation gets to the actual area. Whoa. Let me spread that out a little bit here. There we go. Okay, so if we used 10 rectangles instead of 5, and we had a lot less space extra. Okay, if we were to double this again, 20 rectangles, go 100 rectangles, 1,000 rectangles, we use more and more rectangles, at some point we're going to get really, really, really close to the actual area under this curve. Okay, and this is the concept that we're going to be applying to be able to find exact area under a curve. Okay, so let's go ahead and look at the next page here. So sorry, this one's kind of blurry, not a very good copy of this one, but you have your notes, so be sure to refer to those. So basically, as we're taking more and more rectangles, the area is getting closer to the actual area. So what we do is we say, what if we take the sum, the left-hand sum and the right-hand sum, and we let the number of rectangles approach infinity? And we say that by taking a limit of both the left-hand sum and the right-hand sum. We take the limit as n approaches infinity. Okay, so as the number of rectangles approaches an infinitely large number. Then, as the number of rectangles heads towards infinity, the approximation gets better and better and better, and it's just going to keep getting closer and closer forever to the actual area. So if we take the limit as n approaches infinity of all those sums of those rectangles, that's going to be equal to the actual area under the curve. Okay, so we take this sum as the number of rectangles goes towards infinity, that gives us the actual area under the curve. Okay, and so this is kind of the big concept that comes up that we're going to be diving into throughout this chapter, is just determining that exact area. Using limits here, but then we're going to see ways that we don't need to incorporate the limits so much later on. Okay, so but this is one of the big ideas, is that if we take the limit as the number of rectangles goes towards infinity, the rectangles get so small, it gets so close to the actual area of the curve that eventually it just becomes the area of the curve. Okay. Now, notationally, symbolically, we use summation notations. This is a Riemann sum to identify this. So we call it also sigma notation. But that's this symbol down here just means we're taking the sum as I goes from 1 to n of the function values for x sub I minus 1 times delta x. So this piece inside here, inside the sum, that's just our area of our rectangles, right? This is just our height times width of the rectangle. And what this symbol tells us, this summation notation here, that tells us add up all of the values of this function, I starting at 1 and going up to n. So if I is 1, that gives us x sub 1 minus 1, so that gives us this, f of x sub 0 delta x, plus I goes up to 2, and then that gives us this. I goes up to 3, I goes up to 4, etc., until I makes it up to n, and that gives us our last term. So this notation, the summation notation, it doesn't do anything different. It's just a quicker, more condensed notation, another way of writing the same thing a little more simply and a little more shortly. Is that a word, shortly? So, same thing for the right-hand sum. So you see here I going from 1 to n of f of x sub I delta x. So that's using all the right-hand endpoints. Add up all of those terms. That gives you that area under the curve. So if we were to take the limit of these right-hand sums and left-hand sums, and then that would give us the exact area under the curve. Now, there are other ways of computing area under a curve, other approximation techniques. We're going to look at just one of them right now. So we can also pick a different point. Rather than just the left-hand side or the right-hand side, we can also use points in between. And one point we do like to use is the midpoint of each subinterval. This is denoted m sub n. Okay, so that's what we're going to look at for this example, but this can actually give us a good approximation, and you'll see why in just a second. So here we have the function e to the negative x from 0 to 2. Estimate the area using the midpoints of 4 subintervals. Okay, so n equals 4, so delta x is 2 minus 0 over 4, right? So that's just 1/2. So let's see here. So starting at 0, cutting it into 4 pieces, like that. But we're not going to use the left-hand side or the right-hand side to create the height. We're going to use the midpoint. So that's going to be these in the middle here. Okay, so that's, let's see, 0, that's 1/2, that's 1, that's 3/2, right, 1.5. So this is going to be 1/4 and 3/4, 1 1/4, which is 5/4, right, or 1.25, and then 1.75, so 7/4. Oops. 7/4. Okay, so these are going to give us our height. Right there. And then we can go ahead and draw the rectangle to match. As best we can. Okay, so there's that height. Okay. So this is the area in question. So we're finding these 4. So to get these, let's go ahead and set this up. So there's 4 rectangles, so that's m sub 4. So that's going to be f of 1/4, so f of 0.25, times delta x, which we saw was 1/2, so times 0.5, plus f of 0.75 times 0.5, plus f of 1.25 times 0.5, plus f of 1.75 times 0.5. Okay, and then just plug these into the actual function, so that's going to be, oops, okay, let me go ahead. So you'll notice all of these have the 0.5 in them, so let me go ahead and just pull that out to the front so we don't have to keep writing it over and over again. Then this gives us e to the negative 0.25 plus e to the negative 0.75 plus e to the negative, oops, to the negative 1.25 plus e to the negative 1.75. Okay, and that's really as far as we could go without technology, but we do have technology, so we can approximate this as approximately 0.856 would be the area under this curve. Okay, and again, it's not exact, it is just approximate, but I would say that this is a pretty good approximation. The reason the midpoint rule gives us such good approximations is because we have, because of its being a midpoint, we are going to be working with some left hand, some right hand. So notice here in the first rectangle, we've overcounted this area, but we've also undercounted this area. And in the second rectangle, we undercounted and overcounted. Here we undercounted, overcounted, undercounted, overcounted. So these areas here are not necessarily going to balance out. They're not going to be equal, but this is going to put us a little bit closer to the actual area because we have some parts of it are too low, some parts are too high, so they'll balance out fairly well. Right? Again, not exactly, but they will balance out to a certain degree. Okay, so this is a pretty good approximation of that area. Okay. All right, so now let's go ahead and take a look at the application portion of this section. So we can discuss distance as area under a curve. So remember that distance equals velocity times time, but when we are looking at a graph of velocity, we can use the area under that velocity curve to determine the distance traveled. So here we have, as the car is accelerating, we measure its speed every 2 seconds to obtain the data in the following table and estimate how far the car has traveled during this time. Okay, so what I want to do is I want to look at the graph first. So here we have the plot of the velocity data from the previous example, and there's a curve connecting them. What I want to do is I want to just look at what would happen if we drew our rectangular approximations for these. So it was every 2 seconds, right? So go like this. Oops. So every 2 seconds here. Okay, then if we're going to be doing a left-hand sum, that's going to be down here, and that's going to give us these areas. Okay. So that's going to be our left-hand sum. Looks like an under approximation, right? An underestimate. But if we do our, if we do a right-hand sum, that's going to come from over here. Okay. Now in this case, we actually have an over approximation, right? Because we pick up all this extra area plus all that area. So here we have now an overestimate. Okay? But these areas are giving us area under the curve equals the distance traveled. So again, we're doing approximations, so we won't have exact distances, especially in this case because we only have particular data points. We don't have specific functions to follow through on this. But we're going to find these two areas, and we can look at the boundaries, kind of. We know that the distance traveled must be greater than, right, these lower values, and it must be smaller than these higher values. Okay, so let's go back and let's take a look at this algebraically. Okay, so let's see what we have here. So every 2 seconds, so that tells us that our delta t, we'll use t this time because we're talking about time, is 2. That's 2 seconds. And the number of subintervals, right, is from 0 to 2. That's 1, 2, 3, 4, 5. So n is 5. So let's get our left-hand sum first. So L5, that's going to be f of 0 times delta t plus f of 2 times delta t all the way up to f of 8 times delta t. Okay, and then we have these function values already, right? So this is 20 times 2 plus 30 times 2 plus 38 times 2 plus 44 times 2 plus 48 times 2. Okay, and now it's just a matter of arithmetic, so this is going to be 360. Okay, so that's our left-hand sum. And then for the right-hand sum, so R5, so it's going to be almost exactly the same, except we're not going to include that first term, and instead we're going to add on the last term. So this is going to be, right, f of 2 delta t all the way up to f of 10 delta t. So that's going to be 30 times 2, etc., up to, now this time, 50 times 2. And these numbers, if you add them up, are 420. So, to answer the question, the distance traveled during these 10 seconds must be between 360 feet and 420 feet. Okay. So same computation, so nothing really different here, except now we're just kind of putting a different shell on it. Right? We're looking at it through a new context, but we're still computing the areas of rectangles, adding them up. The more rectangles we have, the better our approximation is, and just remembering that the area under that curve represents a distance traveled, if the curve is a velocity curve. Okay, so if the curve gives us velocity, then the area gives us that distance traveled. Okay. So here they go through kind of the same thing we talked about earlier, just putting it in the context, so everything is in terms of time now, instead of in terms of x values. But you can go through and look over this at your own pace here, but it really is pretty much the same thing as what we were talking about before. Same thing with the summation notation, right? The limit as the number of rectangles goes towards infinity, right? That in this case is going to give us distance instead of area, but it really